Hello, this is the sixth and last session of the second matrix series of OCR Pure Core AS Further Maths. Today we'll be looking at invariant lines and points. When we looked at transformations such as reflections, rotations in 2 dimensions and 3 dimensions, and also enlargements, stretches and shears in 2 dimensions previously, you may have noticed that some points or lines were not changed by the transformation. That is to say, they were invariant. So, for example, when we looked at a shear represented by the matrix 1, 0, 2, 1, and we looked at the effect on the point 0, 1, we found that the image of that point was 2, 1. However, if we looked at the effect of the shear on 1, 0, we found that it remained the same or was invariant. So therefore, the initial point and its image were identical. If we look at another example below, we can see that the matrix 5, 2, 4, 3 acting on the points or coordinates 1, 2 would map 1, 2 to new coordinates 13, 8. However, that same matrix acting on 2, minus 2 does not move it. So 2 minus 2 is an invariant point under the transformation represented by the matrix 5, 2, 4, 3. So how might we go about finding invariant points for a particular matrix? Let's start by thinking about the fact that matrix transformations have all been linear. You may or may not have noticed that the origin never seems to change or be transformed. Let's generalize this by looking at any matrix and seeing that whatever A, B, C and D are, we will always only get the origin again as the image as well as the original point. Let's look at this algebraically. If we have the matrix 5, 2, 4, 3 acting on xy, where xy is such that the image is the same, then we can set up some simultaneous equations. So the matrix multiplication would give us 5x plus 4y is the same as x, and 2x plus 3y equals y. If we rearrange this, we get that 4x plus 4y equals 0 and 2x plus 2y equals 0. Hopefully you can see that if we divided that by 4 and that one by 2, we would get the same line, x plus y equals 0, or y equals minus x. Therefore, in effect, there's an infinite number of solutions to the question, well, what are the invariant points under the matrix 5, 2, 4, 3? And we have a line of invariant points, or all the points on the line y equals minus x will be invariant. Therefore, we can say for the transformation matrix 5, 2, 4, 3, there is a line of invariant points with the equation y equals minus x. If we look at GeoGebra, and you can see here that the matrix M 5, 2, 4, 3 has been set up, and we've also set up sliders to look at various lines. So for example, the red line is y equals mx plus c, where we can use the sliders M and C to vary them, and then the image, the green line, is where the points are transformed to under matrix M. and then the points P and the images P dash are given in blue and red. So let's try and see what happens as we vary M. You can see that the lines and the points where they transform to are changing. Now we thought that when M was -1, that indeed, well, here we have parallel lines. So the matrix M is transforming the red line to the green line. Well, we expected it to be exactly the same line. So let's just check and see by changing C down to 0. If I can manage that. Then, yes, indeed, there we have the line y equals -x is an invariant line, and the points P all map exactly to the same points as their image. Are there any others that do this? Any other lines? Well, I'm going to have a look and see by sliding along. Okay, so not if it's more negative. Let's have a think about if it becomes positive. So there we have, actually, and interestingly, when M equals 0.5 and C equals 0.7, we also have an invariant line. However, in this particular instance, we can see that the point P doesn't map exactly to the same image. The image is, as you can see here, the blue and the red values are slightly different. So that's quite an interesting result. So we found, therefore, by looking at the GeoGebra, that not only was this line, the y equals -x, the invariant line, as we expected, where P and P dash were exactly the same, but we also, interestingly enough, found a line that y equals 0.5x plus 0.7 was also invariant, but in that case, in those cases, the P were not equal to P dash necessarily. So therefore we can see that although an invariant line is mapped onto itself by a transformation, some individual points on a particular line may not map onto themselves. Alright, so it's worth repeating that on some invariant lines, the points P map onto themselves, but not on others. So there's a distinction between then an invariant line and not a line of invariant points. So then if we had, for example, a matrix that represented the transformation of a reflection in the line y equals x, then have a think about that. You're probably already saying, well, surely anything along that mirror line, that reflection line, will be invariant. However, it might also be interesting to consider, well, are there any other invariant lines? Right, so here we're back into GeoGebra, and we've got, we can play around with M, as you can see, and we were thinking that y equals x, if that's going to be a reflection, then we would have an invariant line, but obviously for that then C has to be 0. Okay, and there you can see that indeed you've got your invariant line, and the images P and, sorry, points P map directly onto their images, same thing, P dash. Right, so that's confirmed that would be an invariant line. Let's have a look and play around with M and see if there are any other lines in the scale we've got here where we think, oh, actually that might be another invariant line. So let's have a look. M equals -1 is as well. Alright, so that would be the line y equals -x. Let's look and see if the value, last time the value of C mattered, let's look at the value of C now. Oh, actually, that's really interesting again. So any line where M equals -1 and C is any value is also an invariant line, but note that the points P do not map directly onto themselves, that the images P dash are separate. Okay, so to sort of think again or summarise what we've just seen on the GeoGebra, we were expecting under this reflection in y equals x, which is this matrix M, we were expecting the line y equals x, or if you like the reflection or mirror line, to be invariant, and we found that was the case. But also, in addition, we found that any line y equals minus x plus any value of c was also invariant. So by using GeoGebra, we've thought about this geometrically, and you can see what a dynamic tool GeoGebra is. If you want more notes on finding invariant lines algebraically, please go to the Integral website. This was the last video in the Matrices 2 series for OCR Pure Core AS Further Maths.